Good afternoon, ladies and gentlemen, and firstly thank you all for coming along to hear me this afternoon. I don't have any bicycles or anything else, but what I do have is a lot of data on how 3D printing affects the structure and metrology characteristics of 3D printed items. Okay, the questions that we set ourselves, and this is very much work in progress. We are still carrying out this work. So this is a subset of data. Are digital copies, which is what 3D printing is based on, are they identical to each other? If not, what are the differences between copies, particularly copies made on the same machine as part of a sequence of runs, and also copies made on different machines using as close as possible to the same parameters. I'm limiting myself here, I should say, to metal 3D printing, metal additive manufacturing. Also asking, are there anomalies in what are apparently symmetrical features on an object? And does all of that combined affect the viability of additive manufacturing as a serious manufacturing tool? It's quite a provocative statement. Okay. We've done this work in conjunction with the National Physical Laboratory. Their main offices are in Teddington in London, or just outside London, but we are lucky in the 3M Centre in Huddersfield to actually have their northern hub, which means I don't have to go very far to have very accurate measurements taken. We've used as an example object the NIST, that's the American equivalent of MPL. There's the National Institute of Standards and Technology in the United States. They have a standard 3D printing object, and there's an example of it on the slide behind me. It's a particularly uninspiring object, but it is very well characterized in terms of its dimensional analysis. So it makes a very good tool for the analysis here. Now, if you'll bear with me a second, I've got some of these I brought with me. Right, I have here, I usually try and do this talk a bit like a TED talk, and I throw things into the audience. I've lost too many members of the audience by throwing this one. This is steel. It's quite heavy, but there is a plastic one here that I prepared before the show. This is an SLS version, and I will pass this round. Here we go. That is the NIST standard object. If I threw the metal one, I might kill somebody. I can pass it round if you like. Excuse me. There we go. You can see that it's a fairly uninspiring object, but it's very good for measuring. It has a number of features on the surface, and you see as it comes round. Some of these are upright raised features, and some of them are embossed into the structure. We generated a considerable body of data. This is part of one page of data, and there are 59 pages of data. Now, before you all panic and head for the door, I'm not going to go through all of this data. Just giving you an example of the sorts of things that we've done. We looked at 3 plates, we're calling these objects plates, 3 plates that are made on the same machine, one after the other. And we also looked at 3 other plates made on different machines by different manufacturers. Now, I won't mention who made which. I am grateful to the manufacturers, and if there are any of them in the audience, I can see one at the side there. I'm very grateful for the work they've done on our behalf. I'm also grateful to MPL. But there is a lot of data there. So I've simplified it for this afternoon. We've looked at 5 features. And on the chart, we see X1 is a vertically upwards pillar. Y8 is a similar feature, and X5 is a similar feature. The difference between those are where they are on the plate. So X1 and Y8 are near the perimeter, and X5 is near the center. SN1 and SP2 are identical but opposite features. N1 goes down into the plate, P1 goes up. Okay. First set of data that we looked at is the differences between the diameter of post X1 on 7 different measurements, and we can see that there is a slight variation between the measurements on different circuits. The flatness of the top of the feature has been measured also, and again you can see that there is variation. It's not massive variation, but there is variation. If we look at X5, we get a similar picture. There is variation. If we look at comparing the two features, this is where it starts to get a little bit more interesting. The diameter measurements are virtually the same between the post X1 at the edge and post X5 near the center. But the top, the plateau at the top of the pin, is significantly different. It is smaller, lower, for the post X5 in the center of the build than for post X1 at the perimeter. So that's telling you that if, depending on where your object is in the build, it may actually give you a different measurement. We added into that Y8, it's just because it's exactly identical, if you like, to X1, it just happens to be on the other side of the plate. What you can see there, again, the diameter of the feature, it is a circular column. The diameter of the feature remains virtually the same for each of those 3 objects. But again, as in the previous one, the X1 and Y8 on the outside edge of the build are virtually the same, but the flatness of the top of the post near the center, it's slightly lower. We're talking about, a very small difference, but it is a difference that can be measured. Okay, I'll skip through this very quickly. Effectively here, we're looking at the feature that goes into the plate and a feature that comes up out of the plate. Again here, the positive, that is the one coming up out of the plate, fairly good agreement. The one going down, fairly good agreement. Interestingly enough though, the one at the bottom, the graph at the bottom is showing you that the plate, the bottom of the well that you've created in the metal, isn't flat. It's because on one side there, it's actually a different height from the other side. So there's a slight incline on that plate. One of the other things that we've looked at is the lateral holes in this object. And you notice along the side here in the picture, there are a number of shapes that are horizontal in the side of the plate. We've taken the data, and again I've filtered this data for the this afternoon to cut down on how long I speak, obviously. We've concentrated on the circular hole. Circular hole here, this is for piece A1, that is one of the triple pieces made, the first one made, and you can see here that the solid circle is the measurement as reported. In other words, that's what it's supposed to be. But you can see on all 3, this is at various depths down that feature. You can see that it isn't quite circular. Now again, it's a very slight difference, but if you are engineering something for precision, this could make a difference. Equally, it's interesting, I think, that if you look in the Y-plane, that's the up-down plane here, there is a slight tendency for the shape to be distorted upwards. Now this could be something to do with the recoating process in metal AM, might not be, we haven't got enough data yet, but it could be. Looking between 3 different points, features between pieces A1, A2, A3, these were all printed one after the other. And again, you see very similar feature. There is a tendency for the object to be slightly swept upwards in the way it's been measured here. If you superimpose those, you can see that they're all roughly the same, but they all have the same features, a distortion in the Y plane, that is the up-down plane. Okay, again, more data looking at objects that are going from, these are different machines, and again, if you superimpose them, in this case, you see that there is more difference between the objects than there was with 3 objects from the same machine. But again, a very similar pattern of distortion. Okay, finally, we're going to say, going back to the questions that I set out at the beginning, is the assumption that repeat copies are the same? The answer to that is no, they're not. They depend upon the conditions pertaining at the time of the actual build, the machine that's being used, and also all sorts of other variations. It's not a good assumption to say that digital copies are identical. There are anomalies in the symmetrical features. There are anomalies, such as I showed you in the previous slides, of slight distortions depending on the way the object is built up. Additive manufacturing is a cornerstone technology. I don't think there is any doubt about that. You only have to walk around outside this hall to see that there are scores of companies now investing heavily in the digital manufacturing process. We ourselves are in the process of purchasing something in the order of £750,000 worth of equipment. And we would not be investing in it if we didn't believe in it. But I think you have, and our clients already do, you have to realize that there are limitations to it. You have to work within those limitations. Work in progress, and I mentioned at the beginning that we're doing more. Firstly, there is a huge series of data there. I mentioned that at the beginning. So you will find that we are looking at this over and over again to analyze using various computing technologies to see what we can get out of that data. But interestingly enough, we're also working with our colleagues in the University of Huddersfield who have expertise in X-ray CT scanning. I don't know if Paris is in the audience here, but he is. I know I've seen him at the meeting today. He is doing a lot of work with this same object, but looking at X-ray CT scanning to look particularly at the internal structures, the porosity of the metals as they are built. Now, I'm not an expert in X-ray CT scanning, so I won't try and explain what these pictures show, but it is there to show that there is a lot of information out there on particularly metal AM produced products that isn't yet being explored, and it's one of the things that at the 3M Centre we are very keen to do so. So I think that basically brings me to the end of my presentation. As I said, I didn't have a bicycle to ride through the globes, but if I did, I would have measured it very accurately. Okay, thank you all very much.